So, we're moving on to the exceptions to the octet rule. There's 3 of them there, right? And so the octet rule says that everybody needs 8, and especially the central atom. We're going to give you an example of when there's an odd number, which shouldn't happen, but it does happen on occasion. Those are called free radicals, and they're not good for our bodies because they're trying to find that electron from somewhere, right? So it's going to do some damage to your cells or something like that. And then the next one, there's not enough valence electrons. And then on the last one, there's extra valence electrons on the central atom. And so all those are possible, but they're exceptions. They don't usually happen. So this is a little video by somebody called Dr. B. I guess if I had gotten my doctorate, I would be called Dr. B, but I didn't, and I wouldn't want to. So that's just a little side note. So if you want, I would just wait to copy the structure down till the end, because he's going to be moving stuff around. Okay, and it's a real short, so.
Plus 6 for the oxygen, we have 2 oxygens. So 5 plus 12 equals 17 valence electrons. Nitrogen is the least electronegative, so we'll put that in the center, and let's put an oxygen on it.
Now, he's not going through the whole N, A, S, and U. All he's doing is counting up the A's and then placing them and moving them around. So just so you know.
Either side. We have 17 total valence electrons for NO2. We'll put 2 between atoms to form a chemical bond. Let's go around the oxygens, form octets. So we have 2, 4, 6, 8, 10, 12, 14, 16, and we have one more. We'll just put it right here. At this point, we've used all 17 valence electrons. This oxygen right here has 8, and this oxygen here has 8. So the octets are fulfilled for the oxygens. For the nitrogen, however, we only have 5 valence electrons. We can take these 2 valence electrons here and move them between the nitrogen and the oxygen to form a double bond. And now we still have 8 on this oxygen here. And for the nitrogen, we have 7. For the NO2 Lewis structure, that's the closest we're going to get to having an octet for the nitrogen atom.
Yeah, so there's no other way to you can go ahead and write that down. There's no other way to take care of that lone electron. So it's going to do whatever possible, whatever it runs into or whatever to find that. NO2 is common in smog. Smog isn't as bad as it used to be years ago. One of the reasons we put catalytic converters in cars is because it keeps some of these pollutants from forming. The catalytic converters is good for that. But it's also formed in coal plants and other things. So they're not good for us or our bodies, but they are the exception to a rule. Usually they're going to be paired up. Okay? So
3 valence. This is Dr. D. Let's do the Lewis structure for BCl3. Boron has 3 valence electrons. Chlorine has 7.
And again, I would make sure you wait to the end because he's doing a whole bunch of stuff on here.
Valence electrons. The straw. We'll put boron at the center. And then let's put chlorines around it. There are 3 of them. And put some electrons. So we have 24. We'll put them between to form bonds. There's 6. And then on the outer atoms, 8, 10, 12, 14, 16, 18, 20, 22, 24. We used all the valence electrons on. One problem is that boron doesn't have an octet. The interesting thing is boron doesn't necessarily have to have 8 valence electrons. So I could draw it this way, but I could also draw it with a double bond. So to do the double bond over here, I'll just take these, get rid of those, and put them right here. And that double bond will give us 8 valence electrons for the chlorine and 8 for the bromine. But the question is now, which of these structures is correct? Well, to find.
So what he's going to do is he's going to do something called formal charges, where you look at both structures and you decide which structure is the correct structure based on putting charges on each of the atoms. We're not going to watch all that. You don't have to do that. But I needed you to see both because theoretically you would probably pick the one on the left as being correct. But you'll see as we go through this, as he comes through here, and he starts assigning formal charges to all these. Basically, since all of these have a formal charge of 0 and these don't, this is actually going to be the correct structure. So, like I said, I didn't want you to have to listen to all that. So let's see here. We'll go back. So go ahead and copy that down. Okay, so this is the last one where we have more than 8 valence electrons on the outside. Again, just wait to the end. It's pretty quick here. He'll show you, and we'll talk about it briefly afterwards.
Let's do the Lewis structure for PF5. On the periodic table, phosphorus is in group 5. It has 5 valence electrons. Fluorine, group 7, but we have 5 of those, so we need to multiply that 7 by 5. 5 plus 35, 40 valence electrons. We'll put the phosphorus in the center, and then fluorines, we have 5 of them. Let's put them around like this. We'll connect the phosphorus to each fluorine with a single line representing a pair of electrons, like that. So it means 2, 4, 6, 8, 10 valence electrons. That means we have 30 left. And then we'll fill the octets for the outer atoms. We have 30 valence electrons. 2, 4, and 40.
You like the way you counted it? 2, 4, 40? So what you see there is an exception to the octet rule in the sense that the central atom now has 10 valence electrons. It doesn't happen very often, and it doesn't happen easily. It's one of those things, I think, as chemists, they were always trying to find something new, some new molecule, and so there's ways to force that to happen. But the only reason it can happen is because it's in the 3rd energy level or higher. If you remember, in the 1st energy level, you only have the s orbitals. In the 2nd, you have the s and the p, and the s and the p have the 8 valence electrons. You said those are the bonding electrons. Well, once you get to the 3rd energy level, do we have a 3d orbital? Yes, and so all of a sudden, because there's an extra orbital available, you can force one of the d orbitals to help with bonding. So you can't do this unless it's at least, the central atom's at least in the 3rd energy level or higher. Okay? So go ahead and get this copied down, and we'll move on.